So looking at the next problem, we can either do stuff to the left or do stuff to the right and make it look like the other side, right? It doesn't matter which side you start on as long as you can kind of make them equal to each other at the end. So let's take a look at the left side. So the left side, only really thing I can do is rewrite it in terms of sine and cosine, right? So I'm gonna rewrite this cosine, not in terms of secant, but as cosine x over 1, because that's technically still a fraction, right? And so the reason I want to do that is because it should help me see that I can put them together by multiplying the denominators, right? So I take my cosine on this denominator, multiply it over there, and then I take my denominator here of 1, multiply it over there, and there's a minus between them, so I get 1 minus cosine squared x over, now when I multiply these two together, I get cosine x. Recognize that the top, the numerator, is a identity, and that identity is sine squared x over cosine x. Now, I know tan, on the right side, I know tan is sine over cosine, and then there's an extra sign. So if I were to split the numerator up into sine x times sine x over cosine x, they're still the same thing, right? I'm going to end up with sine squared x in the numerator and cosine in the denominator. But if I do it this way, I know that sine x and cosine x is the same thing as tan x with the sine x in front, which is the same thing as saying tan x times sine x. So looking at the next problem, we have cosine squared beta minus sine squared beta. The beta just means an angle of reference. So initially it looks like we can somehow substitute in this, right? So somehow we can manipulate it, but there's not, because if you notice, we have cosine squared beta minus sine squared beta, which means that this cosine needs to be positive while the sine needs to stay negative. So we can't happen either. They're both positive or they're both negative, right? So that's what's telling me, okay, but that's not an identity. So we notice on the right hand side we have only sine squared beta, right? And so here we have cosine squared beta. So maybe that's telling us maybe we should replace the identity for cosine. So if I replace the identity for cosine, the identity for cosine is equal to, or is the same thing as 1 minus sine squared beta, and then we have the minus sine squared beta here as well. And now if you notice, I have two sines, they both have angle of reference beta and they're both square, so that means that I can put them together, I can combine them, and so I get 1 minus, I have 2 sine squared betas, and that is the same thing as, say, the right side, which is 1 minus 2 sine squared beta. And that's it. That's as far as I need to go, because I've proven that it is an identity, right? So moving on to the next problem, notice how on the right side I have cotan and the left side I have two fractions. So that should indicate to me that maybe I should put them together. Now initially, notice how they don't have any squares, or I can't really split them up, but I can do two things. I can put them together by multiplying the denominators over, right? And then I can also at the same time change that to 1 over cosine theta and see what that takes me to. So I have 1, let's do this. So if I rewrite secant theta, it's 1 over cosine theta, and that is over sine theta, and I'm going to multiply cosine theta and cosine theta. Then there's a big minus sign, and then I have sine theta over cosine theta. I'm going to multiply both of those by sine theta and sine theta. So when I do that in the numerator on the left side, the cosines cancel, I'm left with 1, and then on the right I have the minus sign. On the right side, the numerator, sine theta and sine theta, gives me sine squared theta. And then in the denominator, when I multiply them together, I end up with cosine theta, sine theta. And now we can take it a little bit further, because we notice that 1 minus sine squared theta is in a trig identity. And so that is going to be cosine squared theta over cosine theta sine theta. Now notice how I have cosine theta on both the numerator and denominator. So the denominator one cancels one of the numerator ones, and I end up with cosine theta over sine theta, which cosine theta over sine theta is cotan theta, which is exactly what I wanted to end it up with, and I've proven the identity.